Section 2.3. Other set operations and their properties. Students will be able to understand and explain relations between set operations and logic connectives. Venn diagrams to sort and reason with data. Now, set intersection. We want to consider the following sets. Set C is equal to the set of all x such that x is a college graduate. And set S is all of the values of x such that x earns at least $40,000. Suppose we want to mail a questionnaire to all individuals in a certain city who are college graduates and who earn at least $40,000. Then the individuals to receive the questionnaire include those common to both sets C and S. So, if we take a look here, the intersection of sets C and S is the shaded region. And therefore, we would say that this shaded region represents a college graduate who earns at least $40,000. Now, the definition. The intersection of two sets A and B is written with the symbol A intersect B, is the set of all elements that are common to both A and B. So A intersection B is the same as x such that x is an element of A and x is an element of B. Now the key word is and, which implies both conditions must be met. Now let's take a look at an example. A intersect B in each of the following. So we have set A is 1, 2, 3, 4, and B is 3, 4, 5, 6. So the intersection is going to be the following. The two numbers that belong to set A and that belong to B are 3 and 4. Therefore, 3 and 4 are the numbers that are intersection. Now let's take a look at these sets. Sets A goes from 0, 2, 4, and 6. Now remember, there's an ellipsis here, which it continues on. And then set B is equal to 1, 3, 5, and 7, which has dots that are extended on and on. Therefore, we want to find the intersection there. Now, if you notice here, these are the even numbers, starting with 0. These are all the odd numbers. Therefore, we would say that set A intersects B is the empty set because they do not have anything in common. Therefore, we would say that A and B are disjoint. That's what it means for sets A and B to be disjoint. Let's take a look at the next one. We have set A, which is 2, 4, 6, 8. And then set B is 1, 2, 3, 4. Well, in this case here, we know that all the even numbers are going to be listed in all the numbers that are going from 1, 2, 3, 4, and so on. Therefore, we would say what values intersect A and B? Well, it would be all the values in set A. Therefore, set A intersects set A and B. Now, if C represents the individuals with the college degree, and S represents the individuals earning at least $40,000, we can use a Venn diagram to display information. Now, if we know that 4,800 individuals have college degrees, 5,400 earn at least $40,000, and 1,200 have a college degree and make at least $40,000, then we would say we would take 4,800, which is the individuals who have a college degree, and then subtract 1,200 who have a college degree and make at least $40,000, which would give us 3,600. Therefore, 3,600 have college degrees but earn less than $40,000. Now, if we take 5,400 and subtract 1,200, that would give us 4,200, which earn at least $40,000 and do not have a college degree. So here we can see what the Venn diagram looks like. Now, in the middle, we have the intersection. That means that's 1,200 that what? Have a degree and make at least 40,000. Set C are the individuals with the college degree, and we determine that that's 3,600. And then S represents the individuals earning at least $40,000, and we determined that 4,200 of them earn at least $40,000. Set union. Consider the following sets. Set C, again, is X such that X is a college graduate. Set S is X such that X earns at least $40,000. Suppose we want to mail a questionnaire to all individuals in a certain city who are college graduates or who earn at least $40,000, or both. Then the individuals to receive the questionnaire includes those who are members of Set C or Set S. So, in this case here, the union of sets includes all the elements, both in C and S, and that means that everything is going to be shaded. So when you're talking about the union of sets, you're including everything. So that means it's all of them. X is a college graduate, X earns at least $40,000, and those that are a college graduate and earn at least $40,000. So here's the definition. The union of two sets, A and B, written as A union B, is a set of all elements that are in A or in B. So again, here is set A union set B is equal to all elements of X such that X is an element of A or X is an element of B. Now keep in mind with this word or, the key word is or, which implies one or the other or both. So let's take a look at an example here. If we want to find A union B in these two sets, that means you're going to combine every element in A and every element in B, but you don't need to write one element that's repeated. So therefore, we would say A intersect B is 1, 2, 3, 4, and then 5 and 6. Now again, the 3 and 4 is repeated, so we don't need to write that twice. But again, union means that you're going to include every element in the set A and every element in set B. In that case, it'd be both. Now let's take a look at this set. Now we have the set A, which is 0, 2, 4, 6. Set B is 1, 3, 5, 7. So these are, the set A is 0 in the even values, and B is all the odd numbers. But when you talk about union, you're going to include all of them. So therefore, you're going to have A union B is equal to 0, 1, 2, 3, 4, and then continues on and on. Let's take a look at this one here. We have set A, which is 2, 4, 6, and 8, and set B is 1, 2, 3, 4. Now again, with the union, you're including all the elements in both sets. So therefore, A union B is going to equal B because all of the elements are in B that we have in set A. So again, A union B is equal to B since every element of A is in B. Set difference. Now consider the following sets. Again, C is that X is a college graduate, S is X earns at least $40,000. Now, the set of individuals earning at least $40,000 but not a college graduate is called the complement of C relative to S, or the set difference of S and C. Now, the complement of A relative to B, written as B, which is the set difference A, is the set of all elements in B that are not in A. So this is the set difference of B and A such that that all X such that X is an element of B and X is not an element of A. Now keep in mind that this is not a minus. So note that this is not read as B minus A. Minus is an operation on numbers, and the set difference is an operation on sets. So therefore, this is a set difference. Okay, now relative complement. The set difference to B and A is equal to B intersect the complement of A. This is the set of all elements in B and not in A. So if you look here, all the elements are shaded over here in B, right? But those are all the elements that are not in A. So therefore you can see that all of these elements here have A. We have elements over here that are B, that are in A, but then the ones that are shaded are the elements of B that are not in A. So let's take a look at example 17. Now, if set A is equal to the lowercase letters d, e, and f, set B is equal to a, b, c, d, e, and f, and C is equal to a, b, and c. We want to find the set difference of A to B, the set difference from B to A, the set difference from B to C, and the set difference from C to B. Now, think of how many elements you have in set A. We have 3 elements, and in set B, we have 6 elements, and in set C, we have 3 elements. So, if we want to find the set difference between A and then to B, it's going to be the empty set. Because if you take the difference from D, E, and F to then B, then you're going to have the empty set. Now, if we want to find the set difference from B now to A, well, that means that the only thing that's left over, if we find the set difference by eliminating D, E, and F, what's left over is A, B, and C. So therefore, the set difference from B to A is A, B, C. Now, what would be the set difference from B to C? Well, that means if you have A, B, and C here, and you have A, B, and C here, what do you think is going to be left? Well, what's going to be left now is D, E, and F. So the set difference from B to C is D, E, and F. Now we want to find the set difference from C to B. Well, if we go from C to B, that's also going to be the empty set because you have 3 elements going to 6 elements, and therefore that's going to represent the empty set. Now let's take a look at the properties of set operations. The commutative properties. For all sets A and B, A intersect B is equal to B intersect A, and A union B is equal to B union A. Now, since the order of the elements in a set is not important, it does not matter in which order we write the sets when we find the union or the intersection. Now here's the associative properties. So for all sets of A and B, we have A intersect the quantity B intersect set C. And that's equal to the quantity A intersect B intersect C. For here, we have A union the quantity B union C, and that's equal to the quantity A union B union C. Now, since the order of elements in a set, again, is not important, it does not matter in which way we associate sets when we take the union or the intersection. Now, the distributive property of intersection over union. So for all sets A and B, okay, so if you look here, if we distribute the A intersection to B, then over here, we're going to get the first parentheses is going to be A intersection B. And then we have that union here. And then we're distributing the A intersection to the C. Therefore, in parentheses, we have A intersection C. Now, let's take a look at example 19. We're going to use set notation to describe the shaded portions of the Venn diagrams. So over here in part A, we have set A that's shaded, we have set B that's shaded, but inside it's not shaded. So how are we going to notate this Venn diagram? Well, this would be the following. You would say A union B minus A intersection B. Because this is A intersection B, and if we include all of them, we need to subtract what's in the middle. That's the first option. Another option is saying A union B intersects the complement of A intersection B. Or we would say that the set difference of A to B union the set difference from B to A. Now for this one here, for part B, we have A, and then here is shaded, which is the intersection of A and B. And over here, this is the intersection of B and C. So we would say in parentheses, A intersection B, which is this right here, union B intersection C. Or we can look at this in terms of the distributive property, or factoring out the B intersection. So that would be B intersection A union C. So if we take a look at C here, okay, we can see that A is shaded. So one way of looking at this is the set difference from A to B minus set C. Or we can say set A minus B union C. Or we can say in parentheses set A minus A intersection B, parentheses, minus A intersecting C. Now for D, we can see that there's partial of A that's shaded, we have partial of C that's shaded, and we can see that A intersect C is shaded. So we would say that parentheses, we have A union C, but then we're going to subtract, or not subtract, use the set difference of set B. Union A intersect B intersect C. Or we would say the set difference of A to B intersect C union set difference of C to the quantity of set A union B union A intersect C. Now let's take a look at example 20. Suppose M is the set of all students taking mathematics, and E is the set of all students that are taking English. Identify the students described by each region in the feature. So we have A, B, and C. Well, region A is going to contain all students taking mathematics, but not English, or we would say the set difference of M to E. Now, region B contains all students taking both mathematics and English, or we would say M intersect E. And then for region C, it contains all the students taking English, but not mathematics. So we would say the set difference from E to M. Now, if we take a look at region D, this contains all students taking neither mathematics nor English. So it would be or the complement of M union E, or the complement of M intersect the complement of E. Now, in a survey that investigated the high school backgrounds of 110 college freshman, all following information was gathered. 25 took physics, 45 took biology, 48 took mathematics, 10 took physics and mathematics, 8 took biology and mathematics, 6 took physics and biology, and 5 took all 3 subjects. So, how many students took biology, but neither physics nor mathematics? How many took physics, biology, or mathematics? And how many did not take any of the 3 subjects? Now, to solve this problem, we're going to build a model using sets. So, P is the set of students taking physics. B is the set taking biology. And M is the set taking mathematics. Now, the shaded region represents the 5 students who took all 3 subjects. The lined region represents the students who took physics and mathematics, but who did not take biology. The number of students who took biology, but not physics or mathematics, is represented by the following. The set difference of B to the quantity set P union M. Now, because a total of 10 students took physics and mathematics, and 5 of those also took biology, then 10 minus 5, or 5 students, took physics and mathematics, but not biology. So because 8 students took biology and mathematics, and 5 took all 3 subjects, then therefore 8 minus 5, or 3, took biology and mathematics, but not physics. 6 minus 5, or 1, student took physics and biology, but not mathematics. Now, to find the number of students who took biology, but neither physics nor mathematics, we subtract from 45, which is the total number that took biology. The number of those that are in the distinct regions that include biology and other subjects, that is 1 plus 5 plus 3, or that's equal to 9. So because 45 minus 9 is equal to 36, we know that 36 students took biology, but neither physics nor mathematics. Now, the number of students who took physics, biology, or mathematics is represented by the following. Set P, union B, union M. So the number of students who took physics, but neither mathematics nor biology is 25 minus the quantity 1 plus 5 plus 5, or the answer is 14. The number of students who took mathematics, but neither physics nor biology is 48 minus 5 plus 5 plus 3. And so therefore 48 minus 13 is going to give us 35. Now the number of students who took physics, biology, or mathematics is 35 plus 14 plus 36 plus 3 plus 5 plus 5 plus 1, or 99. Now because the total number of students is 110, the number that did not make any of the 3 subjects is 110 minus 99, or 11. The Cartesian products. One way to produce a set from 2 sets is by forming pairs of elements of one set with the elements of another set in a specific way. Suppose a person has 3 pairs of pants. Set P, pair of pants are blue, green, and white, and 2 shirts, where set S is blue and red. Now, according to the fundamental counting principle, there are 3, which is 3 colors, times 2, which are 2 shirts. 3 times 2 is 6 possible ways to pair an element from set P with an element from set S, forming a set of ordered pairs. Now here you can see that if we have 2 shirts, we have red and then blue, and then down here we have our pants, blue, white, and green. So we have blue, red, blue, blue, white, red, white, blue, green, red, green, blue. Now, because the first component in each pair represents pants and the second component in each pair represents shirts, the order in which the components are written is important. Definition: equality for ordered pairs. The ordered pair xy is equal to the ordered pair mn if and only if the first components are equal and the second components are equal. A set consisting of ordered pairs is an example of a Cartesian product. For any sets A and B, the Cartesian product of A and B, written as A Cartesian product B, is a set of all ordered pairs such that the first component of each pair is an element of A and the second component of each pair is an element of B. So, the Cartesian product of A and B is equal to all the ordered pairs xy such that x is an element of set A and that y is a element of set B. Now note that the Cartesian product of A and B is commonly read as A cross B and should never be read with A times B. So let's take a look at this example. It says if A is equal to, or set A is equal to A, B, and C, and B is equal to 1, 2, and 3, find each of the following. We want to find the Cartesian product of A and B. So to find the Cartesian product, that means that we're going to have a set. We have an ordered pair A to 1, the second order pair A to 2, the third order pair is A to 3. Next, we have B to 1, B and then 2, and then B and then 3. Again, all of ordered pairs. And the last one, we have C to 1, C to 2, and then C to 3. Now we're going to go the other direction. We're going to go from the Cartesian product going from now B to A. So from B to A, now we're starting with the numbers. So we're going to go 1A, 1B, and then 1C. And then we have 2A, 2B, and then 2C. And then we have 3A, 3B, and then 3C. Now, if we go ahead and do the Cartesian product for A to A, we would say A then A then B, A then C. And then we're going to have B to A, B to B, B to B, and then B to C. And then we have C to A, C to B, and then C to C. Now the Cartesian products. It is impossible to form a Cartesian product involving the null or empty set. Now suppose set A is 1, 2. Because there are no elements in the empty set, there's no ordered pairs xy, with x being an element of A and y being an element of the empty set. So therefore we would say that the Cartesian product of A to the empty set is equal to the empty set. Similarly, we would say that the empty set as a Cartesian product of A is equal to the empty set for all sets of A.